Today we're going to look at gas stoichiometry. Gas stoichiometry is really nothing more than combining what we did first semester with stoichiometry with what we're looking at in this chapter, which is gases. Okay, if you remember in the first semester, if we had a balanced equation like two hydrogens reacting with oxygen to make water, what the reaction was telling us is that these numbers in the front here, these 2 and the 1 that we would actually have in front of the oxygen and the 2 here, tell us that we have 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of water. So if I have 2 moles of hydrogen react with 1 mole of oxygen, I'm going to produce 2 moles of water. That's what the balance equation tells us. So everything that we deal with when we talk about stoichiometry, the trick is to work with moles. In this chapter we said that the mole is the end, so that's really our key to understanding what we did when we solve stoichiometry problems. Okay, so if we're using PV equals nRT, we're going to use this version where we solve for the moles to find the number of moles of gas that we're working with. So the key here is to find moles and then figure out whatever variable we're looking for. Sometimes we're going to be looking for volume. Sometimes you're going to be looking for pressure. Not too typical that we would look for temperature, but if you could do that as well. Okay, or the number of moles. So those are the 4 variables we're going to do. So whenever we're dealing with gases and we're dealing with stoichiometry, you really want to start thinking about this equation here, that PV equals nRT. So let's take a look at some examples. Is probably the best way we can deal with this. Okay, so what we have here is what volume of oxygen. Alright, what volume of oxygen is needed to react with 100 grams of ammonia? Alright, so I have 100 grams of ammonia, and what I'm looking for is the volume of oxygen. Okay, so I'm looking for the volume of oxygen. Now remember, if I'm looking for the volume of oxygen, then I need to know if I'm using PV equals nRT, I'm going to solve for volume. So that means I have the moles of oxygen, RT, over the pressure. Now if you remember from an earlier lesson, I believe this is back when we talked about Avogadro's law, STP stands for standard temperature and pressure. What standard temperature and pressure are, if you see STP, the temperature is always 0 Celsius, but remember we have to convert that to 273 Kelvin, and our pressure is always 1 atmosphere. Okay, so that's a quick way of writing the temperature and pressure. And the reason why they use this is that most of the laboratories that we work in are going to have these conditions set so that we can work with the gas laws. Okay, it makes it a little bit easier to work with them. And I'll show you a shortcut you can do when things are at STP. Okay, so if I'm going to solve for the volume of oxygen, I know what the pressure is. I know what the temperature is, so I got those 2 variables. What I need to find are the moles of oxygen, and that's where the balanced equation comes in. What I'm going to do is use the mass of the ammonia to find my moles of oxygen. That's really what I'm going to do here. Because if I have 4 moles of ammonia, then I need 7 moles of oxygen. Well, since I have 100 grams, the first thing to do is get rid of the 100 grams of the ammonia, and I end up with 5.869 moles of ammonia. Well, I don't want the moles of ammonia. I want to keep going because I want to find the moles of oxygen, because if I know the moles of oxygen, then I can find my volume. So what I can do here is I can take that 5.869 moles of ammonia, and this is all from first semester. This is just strictly stoichiometry. So if you need to, go back and watch the first semester videos on stoichiometry to help you along. And I'm going to convert this to the moles of oxygen. So that would be a 7 to 4 ratio. When I end up calculating that, I get 10.27 moles of oxygen. Alright, so now I have my moles of oxygen. Now I can come back here and I can plug back into my equation. And when I do that, I can say that my volume of oxygen is equal to, so my final volume for the oxygen comes out to be, when I've finished doing that calculation, comes out to be 230 liters of O2 is required. So figuring out this solution gives me that answer. Okay. Now, how do I know that it's in liters? Because don't forget R, which I didn't write the units because I kind of ran out of space here, but don't forget the units for R, the one I chose, are atmosphere, so those cancel. Moles, Kelvin, and then leaves me with liters, and that's why my answer is in liters of oxygen. Okay, so 230 liters. Now, one thing you can do, because of the fact that we're at STP, and I'll show you another way to do this problem with this. I don't like this method too much because it's only works if you are at STP. So you have to be at STP for this to work. Ideal gas law, PV equals nRT, always works regardless of whether you're at STP or not. So if you don't like this, I'd stop the video right now and I would just continuously do what I do right now, because this is what I'll do. I'm not going to really do the shortcut. I'm just going to show you the shortcut because some people like it and some people want to use it. So if I have the moles of oxygen, which I have already calculated, so I have my moles of oxygen, I can use that at STP. When I'm at STP, what that means is that if I have 1 mole of oxygen, or of any gas, okay, in this case I'm going to say oxygen, then the volume is always going to be equal to 22.4 liters of oxygen. And this is true for any gas. I could put in here ammonia, I could put in here nitrogen dioxide, I could put in here water vapor. It doesn't matter what the gas is. This is always true at STP. Why? Because if you plug in PV equals nRT and you solve for the volume, which would be nRT over the pressure, and you plug in 1 atmosphere and then you plug in the temperature, 273 Kelvin, and you plug in 1 mole, you're always going to get the answer of 22.4 liters every single time. So that's why you get this little shortcut. And the reason why that's useful is that I don't need to use PV equals nRT. Is really what I'm doing is I'm skipping this step right here where I calculated this. So 22.7 moles of oxygen, and then I would use this as my conversion factor, and I would say I have 1 mole of oxygen, 22.4 liters of oxygen, and if I do that calculation I end up with the same answer, 230 liters of oxygen. Okay, so it's a shortcut, but it only works, it's only as true at STP. This always works, so I would prefer to use that if it were me, but again, just wanted to show it to you. Alright, again, if you want to stop the video, you can stop the video at this point, but I'm going to show you one more shortcut you can do with gases if you want. Alright, so the other shortcut is if we have in this problem, what we're looking for is we're looking for the volume of nitrogen dioxide. So we're looking for volume of the nitrogen dioxide, and we're given the volume of oxygen, 3.56 liters of O2. Okay, so we know the volume of the oxygen. We want to find the volume of this when the ammonia is in excess. So the oxygen is going to go to 0. So there would be, you could have some limiting reactant problems here. And again, we're at STP. So what am I going to do? Well, if I have a gas here, notice that I have a gas right here. This is a gas, and this is a gas. This shortcut only works if you have 2 gases that you're converting to, because if we look at the ideal gas law, PV equals nRT again, and we look at volume, nRT over pressure, well, the only thing that's going to be different is the number of moles, right? The temperature and the pressure are the same. So if the temperature and the pressure are the same for both gases, and the temperature and pressure don't change, then it really comes down to the difference in the moles. Well, this is the number of moles, right? So I could put in a 7 and a 4. Really what it comes down to is that when we say that there's a 7 here in front, we could say that that 7 moles of oxygen is equal to 4 moles of nitrogen dioxide. Or what we can say is that it's 7 liters of oxygen equals 4 liters of NO2. It's a little shortcut that we can use to convert between our gases, as long as they're gases and as long as they're at the same temperature and pressure. Okay, this is the only time this will work, is if the temperature and pressure. Again, here's the thing here: shortcuts can throw you off, so be very careful with these shortcuts because they're very conditional, meaning that you have to have certain conditions that are met. All right, so I'm going to go ahead and show you how I'm going to do this. I'm going to take 3.56 liters of oxygen, and I go from the liters of oxygen, because we now said that the 7 liters of oxygen is equivalent to 4 liters of the nitrogen dioxide. So what I can do now is I can just take that 3.56, multiply it by 4, and divide it by 7, and I can end up with the answer of 2.03 liters of nitrogen dioxide. Now, if you want to prove that this is going to work, what you could do is you could say, okay, I have this, and use PV equals nRT, right? Use this here, this equation, and use PV equals nRT to solve for the moles. Moles are equal to pressure, volume, R, and T. And when you get that number of moles of oxygen, then you can convert to the moles of nitrogen dioxide. But since that's where you're going to get the 7 and the 4, and then you can come back and convert that to liters, well, you're going to use PV equals nRT again, and the temperature and the pressure cancel out on both sides. So if you want to, you can do that step where you convert to moles, convert moles of oxygen to the moles of nitrogen dioxide, then use the volume version, volume equals nRT over pressure, and then you could find the mole volume, and you'd end up with 2.03. Or you can just trust me that this will work. Alright guys, that's pretty much it for gas stoichiometry. We'll get some practice in class. See you later.